So zooming back out just so we could see this first one here. So for the first one here, let's do, I'll do a different color of ink for each one. So let's do A, where our y equals 0, or y of 0 equals 1. So that's telling me my x is 0 and my y value is 1. So where does that occur, right? And so if x is 0, that occurs on this line, if I could draw it straight, right? And when y equals to 1, that is about right here, okay? So what that's saying is our point then is this point right here, and we want to follow this directional force here, so to speak, to help us get what is the shape of that curve. And so you could see that it might be coming from this direction if you're looking at the arrows, and then it shifts and comes back. Let's say it comes here, it starts shifting down. Now we're here and maybe shifting back upward. Okay. And I'll take these extra lines that helped us to look at that. So that's kind of essentially how we would map that first one. So let's get another color for when y of 1 equals 0. So that tells me that my x is equal to 1. So that occurs roughly right here. And when that happens, we're looking at a y equal to 0. So that is right here. So that intersecting point is this dot here. So we can look at that. And now what does that direction or that directing field tell us here? And so here we could see that this arrows, you could see, kind of lead us like this. And these arrows, maybe we could come up in that opposite direction. So you kind of just follow those arrows along to see how they are. So we probably did this pink line here down just slightly a little too far, but these are all just handwritten approximations. And so that is okay. All right, let's look at the next one. Let's go with another color. So here we're looking at x and y, both are 3. So, oops, that's -3. So here is y is equal to 3. Here our x is equal to 3. So we would be starting out at this point here. So what is this force field telling us? We can see that we're going up here, and then we're just following this around in that direction. We can take out those extra lines, and that's roughly what that shape of the graph is going to look like. The last one example we have here is when our x is 0 and our y is -2.5. So here's -3. So this is going to be y equal -2.5. And then our x is equal to 0. That occurs right here. We can put that in here. And so what is this force field, like this directing force? You could see that the arrows lead us to something about like that. Okay. And I'll actually blow it up a little bit more so you guys see that. Yeah. Okay. All right, let's look at the next kind of problem. I'm going to just go with the black font. So here, this is out of section 2.2. It's asking us to find an explicit solution of the given initial value problem. So we're given this problem here. We can say that let's go ahead and rewrite this. Let's put it where all of our y stuff is on the left-hand side and all of the things with an x are on the right-hand side. So if we rewrote that, we're really just going to move this to this side and the dx to this side. Okay, so that's really all we're doing in this first step. So we end up with 1 over y squared minus 1 dy is equal to 1 over x squared minus 1 dx. So now what we want to do is we just want to integrate both sides. So we can, to do that, and the formula used to find the integration, remember, I'll write that over here to the side just as a reminder. We can have, we have dx over x squared minus a squared. And remember that that is equal to 1 over 2d ln x minus a over x plus a. And then let's not forget that constant c. Okay. So when we do this, we end up with 1 over 2 times 1 ln of y minus 1 over y plus 1 is equal to 1 over 2 times 1 ln x minus 1 over x plus 1. And then we have that plus ln of c. Okay. We want to get rid of, we can multiply this whole thing. Like if I want to get rid of this 1/2 over here, I can multiply by 2 over 1. I could do the same. I have to do it to the whole right-hand side. So we could do that. And that leads us to simplifying where we have ln of y minus 1 over y plus 1, which is equal to the ln of x minus 1 over x plus 1 plus 2 ln of c. Okay. When we're doing this, we can actually take this and put it up into the exponent form. Remember, back to thinking about just when we deal with logarithms in general. So this would then simplify to ln of y minus 1 over y plus 1 is equal to ln of x minus 1 x plus 1 plus ln of c squared. Okay. Now, again, using our laws of logarithms, we can combine these two logarithms on the right-hand side. So we have ln of y minus 1 over y plus 1 equals the ln of, since those are addition, right? So that's c squared times x minus 1 over x plus 1. Okay. And if we let our c squared just equal capital C or something so that it's just another constant, we could do that as well. So I'll write that here. We're going to let c squared equal c, which is just another constant. Okay. And so that's going to get us to, well, first of all, when we have an ln on both sides, we can actually, those can cancel with each other. And essentially, we're just left with y minus 1 over y plus 1 is equal to, instead of c squared, we're going to just have it that constant c, x minus 1, x plus 1. Okay. So now we can look at this. We were given the condition where y of 2 is equal to 2. That's telling me that x is equal to 2 and y is equal to 2. So we can plug that up into our formula to solve for c. So we end up with 2 minus 1 over 2 plus 1 is equal to c times 2 minus 1 over 2 plus 1. So that gives me 1/3 equals C times 1/3. Therefore, C is equal to 1. So when we put that value in the above equation, then we get y minus 1 over y plus 1 equals x minus 1 over x plus 1. So essentially, we get that y is equal to x. Okay. For the next problem, this is problem number 30 out of section 2.2 again. And so for this one, we need to find an explicit solution of the given initial value problem that we're given here. So we have what we're initially given. Again, we want to, let's move to do our integration technique. So that is 1 over y squared dy is equal to sine x squared dx. And if we do our integration techniques, then, and we want this to go from, our x value here is -2, but we don't know what it's going to. So we can actually do our integration from -2 to x, because we're not sure how much at this point. And so let's do this in terms of dt. Actually, if we had left this here because it's the explicit and here we can do it as a two-step part. And so we can have 1 over y squared of t dy dx dt. Okay. And then, or if we're letting the x, just let it be x, right? We can have dt here. And so we're integrating both sides from -2 to x. And so this is our sine of, so we're letting our x's be dt's now. And we're following along again. If you reference the textbook, you can proceed as example number 5 in that textbook. Okay. So we'll end up here with -1 over y of t. We're going to evaluate that from -2 to x. And that is equal to that integral -2 to x of our sine t squared dt. Okay. So when we do that right-hand side, left-hand side, when we integrate that, that's going to be our -1 over y x plus 1 over y evaluated at -2. That is equal to, we're still just keeping our right-hand side constant, the same. Okay. Simplifying, we can plug -2 into our original function here. And we were given that y of -2 is 1/3, so we can substitute that out. So we have -1 over yx is plus 1 over 1/3. And I just paste that same form, that same right-hand side. Okay. 1 divided by 1/3 is the same as 1 times 3 over 1. So that's going to equal 3. So we have -1 over yx plus 3 is equal to that same right-hand side. Okay. And then the last thing we want to do is let's move the 3 to the other side, and let's well, we can actually leave the 3 on the side that it is. Let's move this. We multiply both sides by the y. Really, we're just trying to get what is y of x. That's what this problem was asking us to do. So if we multiply that, we end up getting y of x is equal to 3 minus our integral from the right hand side, sorry. But that's going to then be to the -1, right? Because all of that would have been on the bottom, but we're going to bring it up into the numerator and give it that -1 for the inverse. Okay. All right, next question, section 2.3. In this problem, we want to find a general solution and that largest interval. So to determine whether there are transient terms in the general solution of the differential equation, we need to solve the equation and analyze the nature of its terms. Okay, this is a first order differential equation with the form. Remember, first order is y prime plus p of x, y is equal to q of x, right? So this is a first order linear differential equation. So if we take this problem, we can divide all everything by x, right? So if we come here, we want to divide everything by x. So when we do that, we're going to get an equation that looks like y prime plus 1 over x plus 1 times y equals e to the negative x sine 2x divided by x. So now let's identify what is our p of x and our q of x. So in this problem, our p of x is going to be 1 plus 1 over x. It's this piece right here. I've just reordered how we write that so that the constant is listed first. And then our q of x is just what is on our right-hand side, which is e to the negative x sine 2x divided by x. Okay. Now we want to compute our integrating factor. Remember, I'm going to make this a different color as well, but you remember our integrating factor, we could say our m of x is equal to e with the integral p of x dx, right? And that's going to simplify as e integral of 1 plus 1 over x dx, right? We're just substituting in what we have for our p of x. When we simplify that, we get e to the x plus ln of x. And that's going to simplify just to e raised to the absolute value of x, which is equal to x e to the x. Okay. So now we can use that to plug into our problem here. So we have d dx of x e to the x times y is equal to the sine of 2x. And we have that y is equal to negative 1 over 2x e to the negative x cosine of 2x plus c e to the negative x over x. For this is going to be for are x's that are between 0 and infinity. And so that entire solution is going to be transient. Okay, next problem is number 28 out of section 2.3. This, again, looking at our integrating factor for this problem, well, let's identify first what our, so we have this here, we can rewrite this in terms of dx dy minus x over y is equal to 2y squared. Okay, so basically, what we're looking at here is we were just combining, getting a like term there for with the y. So if we look at that, and actually it wouldn't be a y squared because if we're dividing everything by y. So when we look at this leaves us with, so looking at our integrating factor. So our integrating factor is going to be the integral -1 over y dy. So that is e to the negative log of y, which is simply 1 over y. Okay, so we have x times our integrating factor equals the integral of our integrating factor times 2y dy. So now let's substitute that integrating factor into this formula. So we'll copy paste that, and really everywhere we just see this integrating factor, we're substituting in that integrating factor. Okay. So then we end up here with our x over y is equal to, and then when we integrate this, that is going to give me just 2y plus c. That's because, right, we ended up with 2y over y, which is 2. When we take the integral of that, it gets us to that 2y. Okay. So now let's plug that in using what we were given. We were given that y of 1 is equal to 5. So that is 1 equals 2 times 5 squared plus c times 5. And so c is going to be -49 over 5. So we would plug in and have x equals 2y squared minus 49 over 5y. And so that solution is defined on that integral, not integral, interval, where I is equal to 0 to infinity. Okay. This next problem we're looking at is from section 2.4. And we need to determine the given differential equation if it is exact. And if it is exact, then we need to solve it. Okay. So the first thing, let's let m equal sine y minus y sine x. And let's let n equal cosine x plus x cosine y. Okay. So when we take those partial derivatives of m with respect to y, that's going to give us cosine of y minus sine of x. When we take the partial derivative of n with respect to x, that's going to give me negative sine of x plus cosine of y. And when we could rearrange this, right, and see that my partial derivative of m with respect to y is equal to my partial derivative of n with respect to x, right? So therefore, these equations are exact. So now we have to integrate, and let's do so with respect to x. Okay, so we have f of xy equals, we're going to take the integral of sine y minus y sine x dx, and that equals x sine of y plus y cosine x plus some other function. Let's just call it h of y. Okay. Now we want to differentiate with respect to y and compare that to our n function. So if we're differentiating with respect to y, that gives us x cosine of y plus cosine of x plus, then we would be taking the derivative then of y, of hy, and so that's h prime y. Okay. We could rewrite this in a couple of different ways. You could say that that is also equivalent to the cosine of x plus x cosine of y minus y. Okay. And so in this case, we can also say our h prime of y is equal to that negative y. Okay. Given that h of y is negative y squared over 2, and that's, we've integrated h of y with respect to y, right? Remember, if we have a derivative and we want to get back to the original function, we have to take the antiderivative or integration. Okay? Therefore, we can conclude that f of xy equals c, which is x sine of y, that is a better x sine of y plus y cosine of x minus y squared over y is equal to our c. Okay, another problem similar to the one that we just recently did. And so for this one, we kind of want to do along the same lines, right? So if we let m equal our first portion, so the x cubed plus y cubed, and we let n equal 3xy squared. Taking the partial differential equations with respect to, or the m1 with respect to y, gives me 3y squared. And when I take the partial differential with respect to x, I get 3y squared. Again, I can see that my partial differential equations are equal. Therefore, this is an exact, the equation here is exact. And so let's now set our f of x y equal to the integral of 3xy squared dy. Okay, when we integrate this, so if, let's say, so integrate in x of y equal to 3xy squared, right? And we want to do that to find our f of xy. Okay. So when we integrate that, we find out that f of xy is xy cubed plus c. Okay. If we let c equal just that function g of x, Okay. Then we can set the partial derivative with respect to x of our function is going to give us, with respect to x, is going to give us x cubed plus the y cubed, right? And so when we simplify that, that's d of g of x plus y cubed is equal to x cubed plus y cubed. And we want to solve for that derivative. So we're going to solve for this. That gives me dg over dx equals x cubed. Okay, let's get another page here. We want to find the antiderivative of x cubed so that we can find our g of x. So therefore, our g of x then is going to be 1 over 4 x to the 4 plus c. Just that is the antiderivative of x cubed. Now we want to substitute for g of x into our f of xy function. So again, I'll write that over here since it's on the previous page, is equal to xy cubed plus g of x. We'll substitute that into our function here. We have xy cubed plus, we're just substituting in g of x, which was the antiderivative, plus c here. And now we can just rearrange to solve for that and see that, well, we could leave it at that as well. So we would have xy cubed plus 1/4 x to the 4th power plus that c. Okay, one more initial value problem from 2.4. Okay, if we let m equal our e to the x plus y, and we let n equal 2 plus x plus y e to the y. We have my is 1. We also have nx is 1, right? So we took the partial derivatives of each of those. So we can see that those are equal. So our function for x is e to the x plus y, which we can then say that f is equal to e to the x plus xy plus some function h of y, where our derivative of our h function would be 2 plus y e to the y. Therefore, our h of that function would be 2y plus y e to the y minus e to the y. And so the solution then is going to be c is equal to e to the x plus xy plus 2y plus y e to the y minus e to the negative y. And if y0 equals 1, right? So when x is equal to 0, y is equal to 1, then c, let me write for our initial, so y of 0 equals 1, then c is equal to 3. So that is saying we plugged in 0 for all of our x's, 1 for all of our y's, and then our c is going to reduce down to 3. So you could just rewrite this equation here. And instead of having it c equals, that whole equation is equal to 3. Okay, this next problem we're looking at is from section 2.5, problem number 10. We want to solve the given differential equation by using the appropriate substitution. So let's let y equal ux. So we have the square root of x squared minus u squared x squared dx. So all we've done is substitute in ux for our y, minus x squared du is equal to 0. We could simplify this a little bit. You could see each of these terms have an x squared, so we could pull one of those x's out, and that's going to leave us with 1 minus u squared under the radical dx minus x squared du equal to 0, keeping in mind that x has to be greater than 0. Okay? So dx over x minus du over the square root of 1 minus u squared is equal to 0. We're still just simplifying and combining. The derivative of 1 over x is ln of x. And then minus our sine inverse of u is equal to c. Okay? So getting sine inverse of u by itself, that is equal to the ln of x plus c. What we could do here now is kind of think of it as taking the sine of both sides. It isn't really a mathematical transaction like that, but if you could think of it, undoing an inverse is multiplying by it. So we can do that here. So, and also I'm gonna, in the same transaction, I'm gonna replace the u. Remember if y equals ux, then u is equal to y over x. So I'm going to just translate that back in down here. So that leaves me with y over x is equal to the sine of ln of x plus c. And so we can get y by itself, multiplying both sides by x. So x sine of ln of x plus c. Okay. This next problem coming out of section 2.5, we want to solve the given initial value problem. This is problem number 12. So we can rewrite this as dy dx is equal to x squared plus 2y squared over xy. Again, we're going to use substitution here. So if we let y equal u of x, we can take our dy dx equals u plus x du dx. And then we substitute that in above, okay, to give us u plus x du dx is equal to x squared plus 2ux squared over xux. Okay. For the next few steps, we're really going to keep our left-hand side of the equation equal and steady. And so we're really going to just be working on simplifying the right-hand side, so that we can simplify this piece of the right-hand side to x squared plus 2u squared x squared over x squared u. you'll see I have an x squared in all of the terms. I could have also, instead of doing that, I could have done one more step where I factor out an x squared out of the numerator and leaves me with 1 plus 2u squared over x squared u. And then I would have seen I could have canceled it. And I end up with the same thing anyways. Okay. So that is the u plus x du dx. That's my left-hand side is equal to 1 plus 2u squared over u for my right-hand side. Okay. I'm going to minus a u from both sides. Okay. So this gives me, when I minus a u from both sides, this actually gives me here 1 over u plus 2u. Well, when I minus, and then I minus the u from, let's minus the u from there, because this is really just splitting this into this, okay? And then I can minus the u from this. When I do, that then takes me just to 1u in the next step on that, that side. So I have x du dx is equal to 1 plus u squared 1 over u plus u. Okay. I can rewrite this piece here. So this is just taking this, simplifying it to here. I could rewrite this as in where I get common denominator. So that's going to be 1 plus u squared over u. Okay. So now let's put our du and our u's and our x's together. So we're going to have u over 1 plus u squared, right? Because we're multiplying by this reciprocal. And so to move it to the other side. So du equals that. And then this is going to be 1 over x dx to get those from the left-hand side to the right-hand side. Okay. So that is the first step of the problem. Now we need to, let's get another clean sheet and let's let 1 plus u squared equal our t. So for this substitution, so we have 2u du equals dt. Okay. Or that is du is equal to dt over 2u. Okay. We want to integrate both sides. So that's going to give us the integral of u over t dt 2u, which is the left-hand side is 1 over x dx. Okay. And so now when we can simplify that, we can get to the integral of 1, because the u's will cancel, 1 over 2t dt is equal to the integral of 1 over x dx. So when we take the integration of that, we have 1/2 ln of t is equal to ln of x plus ln of c, where ln of c is just an arbitrary constant. And I'm putting the L in there because it'll make doing other calculations here in a moment easier. Because remember, we're just saying some constant out there. And so we're going to just say this one happens to be ln of c. So this gives me 1/2 ln. Now for t, we're going to plug back in that 1 plus u squared from our substitution is equal to ln of x plus ln of c. Now let's move this 1/2 to the other side, right? So 2 times 1, and then not 2 times 1, 2 over 1. We're going to multiply each of those by that, and that is to really just get that we're trying to eventually dwindle down. I'm getting rid of the ln's and such. Okay. So that's going to give us the ln of 1 plus u squared is equal to 2 ln of x plus 2 ln of c. Okay. And we can put that up in the exponent. Okay. This is going to give us ln of 1 plus u squared equals ln of x squared plus 2 ln of c. Or we could say c squared as well, right? And just as with the previous earlier example, c squared or just the capital C, it doesn't matter. It's still just an arbitrary value. So we could actually move this ln to the other side, right? I'm going to just, instead of here, I'm going to say we're going to minus, and that's equal, right? All I've done is move the ln of x from the right-hand side to the left-hand side, so I'm just minusing it off. And so when we combine this, we would have ln of 1 plus u squared over x squared, right? Because remember the rules and properties of logarithms. When you have one logarithm subtracted from another, that's the same as division. So we can do that, and that is equal to the ln of c squared. Now at this point, we can delete or cancel the ln on each side. And we can also let c squared equal c, which is just an arbitrary value. So we have 1 plus u squared over x squared is equal to c. Now we want to substitute our u. So we're substituting back in u is equal to y over x. Okay. So this gives me 1 plus y over x squared over x squared is equal to c. We can rewrite that as x squared plus y squared over x to the 4th is equal to c. We were given an initial condition where, I'm going to see if I can speed this stuff up a little bit, give us a little bit more room. So we have that initial condition where we were given that y of -1 equals 1. So we have -1 squared plus 1 squared over -1 to the 4th is equal to c. So that is 1 plus 1 over 1. So that's 2 over 1, which is 2, which is what our c is. Therefore, we have x squared plus y squared equals 2x to the 4th. Okay. Next problem, section 2.5, number 22. We're asked to solve the given initial value problem again. So we want to divide both sides by y to the 1/2. We really want to just get everything that, because we're trying to get the dy dx by itself. So if we divide by y to the 1/2, we have to divide all terms by that. When we do that, that gives us dy dx plus, if I have y to the 3/2 divided by y to the 1/2, remember rules of exponents, I can bring that up here and just change the sign. So that is the same as saying y 3/2 minus 1/2. So that is y squared. I mean, not y squared, it's 2/2, which is y to the 1. Okay. So that is why we will have here just y. And then this is y to the negative 1/2 because we're just bringing it up to here, right? So this is a Bernoulli equation, right? So just as a refresher, that is our y prime plus p of x y equals q of x y raised to the nth power. Okay, so in this case, our n is negative 1/2. Okay, that's our n is negative 1/2. And so when we go through this, our substitution, substitute u is equal to y1 minus n, which equals y1 minus negative 1/2, which is y 3/2. Okay. So our u prime then is going to be 3/2 y to the 1/2 there. Okay. And our y prime is equal to 2/3 y to the negative 1/2 u prime. Okay. So it could be either way, just in how we rearrange those things. Okay. And so since dy dx plus y equals y to the negative 1/2, we can divide everything. Let's rewrite our original equation. As 2/3 y to the negative 1/2 u prime plus y equals y to the negative 1/2. So we're just looking at this equation up here and plugging in our dy dx that we have. Okay. We can divide everything by 2/3 y to the negative 1/2 because we're trying to get that, isolate that y prime. So we have to do this for all terms, right? Do it for all 3 terms. And that's going to simplify to u prime plus 3/2 y to the 3/2, and that equals 3/2. Okay. If we let u equal y to the 3/2, we end up with u prime plus 3/2 u equals 3/2. Let's take this to the next page. Okay. So du dx is equal to, we're going to just move this to the other side. Okay, is equal to 3/2 minus 3/2 u. So that equals 3/2 times, we're just factoring a 3/2 out of each, times 1 minus u. Okay, now let's get our u's on one side and our x's and constants on the other. So this would be du over 1 minus u is equal to 3/2 dx. We can integrate both sides. Okay. When we integrate both sides, we end up with this negative ln of 1 minus u is equal to 3/2 x plus c. Subbing in where u is equal to y over 3/2. So that would be negative or minus ln 1 minus y to the 3/2 plus equals 3/2 x plus c. And then we were given an initial value. We were given that y of 0 equals 4. So we'll use that. So that's telling me that my x is 0 and my y is 4. So how do we simplify that? We would have negative ln of 1 minus 4 to the 3/2 equals 3 times 0 over 2 plus c. Simplifying a little further, that gives me negative ln 1 minus 8 equals c. So c is equal to negative ln of 7. But we can remember this is like saying it's a negative 1. So we can put that up in the exponent. So that is the same as ln of 7 to the negative 1 or ln of 1 over 7, all just using the rules of exponents. I'm going to scoot this stuff up to give us a little bit more room. Okay. So now we have negative 3x squared, negative 3x over 2 is equal to ln of 1 over 7 plus ln 1 minus y to the 3/2. Okay. And so that will simplify to ln of 1/7, right? We're just combining these two terms. They're added, so they're multiplying. 1/7 times 1 minus y to the 3/2. Okay. We can raise each of these to the e, right? So when we do that, it simplifies, or e raised to each of those. So that's going to give me e to the negative 3x over 3 is equal to these cancel, it leaves me with 1/7 times 1 minus y to the 3/2. Simplifying a little bit further is 7e to the negative 3x over 2 is equal to 1 minus y to the 3/2. Okay. And one last step, we're getting that y to the 3/2 by itself. So we have y to the 3/2 is equal to 1 minus 7e raised to the negative 3x over 2. Okay. Next problem. This is out of 2.6. And there's a couple of problems like this one. And so what I am going to tell you is I'm going to work through a few of the calculations, not going to work through every single one of the calculations for this problem, but I do want to work through a couple of them to make sure that you understand how to use Euler's method to get these calculations, right? So first, Euler's method states that we have this y n plus 1 is equal to y sub n plus h times x sub n squared plus y sub n squared for this problem, right? Because that is our problem, x squared plus y squared. Okay. And we were given here in this problem that h is equal to 0.1 initially. We're going to do it for 0.1 and then we'll do it again for 0.05. We know that our x naught, or our first x sub 0, is equal to 0. And we know that our y naught, or our initial y that we were given, is 1, and we get that from here. Okay. And we're starting out with n equal to 0. That is the number we're looking at. So when I'm looking at n equal to 0, then that is when I'm plugging it into this formula here, n is 0. So then I get y1 because n is 0. So 0 plus 1 is 1 equals y sub 0 plus h times x naught squared plus y naught squared. Okay, so that's what we're looking at. And now let's just plug in the values that we know. We know that y naught is 1. We know that our h is 0.1. We know that our x naught is 0, so 0 squared, plus our y naught, which was 1 squared. Okay, and that's going to simplify to 1.1. Okay. And I'm going to need that for the next level, right? Because when I look at n equal to 1, that is 1 plus 1. So now I'm looking at y2. y2 equals, this is now y1 plus h times x1 squared plus y1 squared. Okay. So this now gives me a value of, we're looking at our x value. I'll show you this next page. Our x values are increasing. It was 0 first, and then we're adding 0.1, and then we're adding 0.1, 0.1, 0.1 each time, right? So when we look at that, our y1, this is our y1 value. So that is 1.1. Plus my h stays at the 0.1 throughout the whole duration of this table that we're calculating. Plus our times, now my x, remember we're upping it once, so now we're on the second iteration, so it's 0.1 squared. Plus my y again, my y1 was 1.1, and we're squaring that again as well. And so when we do all of that, it simplifies. And this problem is asking us to go to 4 decimals. So it's 1.2220. Okay. Y equal to 2, that is going to be my, n equal to 2, that is my y sub 3. So this is y squared plus h. Now that is going to be my x, my second x squared plus my second y squared. So my y2 now is at 1.2220. See, we're pulling that from the previous line. My h is still this 0.1. Now I'm on my next iteration of x, right? So we went 0, 0.1, 0.2, 0.3, 0.4, 0.5. These are the 5 x calculations that we need to make. So we've done this one, we've done this one, and now we're on to this, the third one, which is 0.2 squared plus 1.2220 squared. Okay. And so that's going to give me a value of 1.3753. Okay. And I'm not going to work through y4 and n3 and n4 and so on. I think that gives you a good starting point. I will say that work correlates over here. So you could see we had 1.1, and then, or 1.0, and then 1.1, 1.22, and then we just did that calculation for 1.3753. Okay. Now I'm going to just do a couple to show you how we're getting the second table, right? Our second table here is where we're looking at now all of these initial conditions are the same except our H. So I'm going to just copy that. And our H is actually now 0, 5. Okay. So let's just copy this one as well. We'll make a couple of little edits with it. So for this one, our y sub 0, so we're still 1, but now we're plus, our h is 0.05. Our x is still the same, and our y is the same. And so this gives me 1.0500. Okay. So when I do n equal 1, now I have y2 is equal to y1 plus h, x1 squared plus y1 squared. It's going to give me 1.0500 plus the 0.05 times my x now is, so the next iteration we're 0, 0.5, then we're 0.1, 0.15 all the way down. So this first one is 0.05. Sorry. Okay. So that is 0.05 squared plus my 1.0500 squared. And that's going to give me a value of 1.1053. Okay. You could do that. I'll do it one more iteration, n equal to 2. So that's my y3 equals y2 plus h times x2 squared plus y2 squared equals. Now my y is 1.1053 plus 0.05 times 0.1 squared plus 1.1053 squared. So when we do the math on that, we get 1.1668. And you can continue on just as we could with the previous one. And here's the table that you will end up building. So I would encourage you to go out, practice that a little more, and do those calculations, because you probably will see this type of calculation again in some form, either on a quiz or an exam. Okay. Another problem, just like the previous one, except it's a little bit different, right? So the process is exactly the same. The type of problem is a little bit different. So that's why I wanted to share this with you, this example with you. So let's just come back over here, kind of take this. It's similar to these pieces. And paste that in here. Just so you have the Euler's stuff again. The thing that's going to change now, and the reason I copy and paste it is because I want to show you how that has changed, right? And so for this one, this is our problem here now is y minus y squared. Okay. And so my h, again, we're going to start with the 0.1. My x naught is 0, and my y now is 0.5, and my n is still keeping at, we're going to start out with 0. Okay. So when I look at my n equal to 0, that is going to give me a y1 equals y naught plus h times y naught minus y naught squared. Okay, so that equals, I'm going to just put it underneath here. So my y naught is 0.5 plus my h, which is 0.1, times my y naught, which is 0.5 minus 0.5 squared. Okay, so that's going to give me 0.5250. When I look at n equal to 1, that is going to be my y2 equals y1 plus h times y1 minus y1 squared. So that gives me my y1 value is 5250. It's 0.5250 plus my h is 0.1 times 0.5250 minus 0.5250 squared. That's going to give me a value of 5747. And you'll want to just continue this on until you get through all of your n. Okay. Fill out the table. Okay. So again, same idea. Instead of our h being 0.1, now we want it to be 0.05. Okay, so we're looking at the second one. So different color. So our h is now 0.05. The rest still stays the same. So my n equal to 0, now I'm going to have y1 is equal to y naught plus h times y naught minus y naught squared. Okay. My y naught is the 0.5 plus 0.05 times 0.5 minus 0.5 squared. Okay. That's going to give me 0.5125. Let's do one more. N1 is going to give me y2 equals y1 plus h y1 minus y1 squared. So that gives me 0.5125 plus 0.05 times 0.5125 minus 0.5125 squared. And that's going to give me a value of 0.5250. You can carry that on as well, and you will end up with a table like this one. Okay. And you'll notice that in the beginning, these stay very close and true to the previous table, right? So you'll see that 0.1 is, they're the same value in both tables. But when you get down to around 0.3 right here, you'll see that they start separating a little bit. So when you're looking at that, just know that you can't carry on, you can't just only calculate the 0.05, 0.15, etc. Because eventually there's enough separation that the decimal value is different. If you look at the 0.5, you'll see that the y value is different. Okay, a couple of more problems. This is coming from the chapter review. This is problem number 20. So we are given the problem here. So let's just move everything. What we're going to do is we're going to combine these terms here, the ln stuff. And so we get y, I'm going to change the ink to black. We get y not equals y times ln of x over y dx is equal to x ln x over y minus y dy. Okay, so dx dy is equal to x over y minus 1 over ln of x over y. If we let u equal x over y, then that's the same as x is equal to u times y. So dx dy is equal to u plus y du dy. Okay. This we could then say u plus y du dy. We're just writing the left on the right and the right on the left, but we're also, instead of dx dy, we're going to substitute in this portion of it as well. And so we can say we have the u plus y du dy is equal to, well, let's plug in this portion, u minus 1 over ln of u, following along with those substitutions. So now we can simplify a little bit more. We have y du dy is equal to 1 over ln of u, or negative 1 over ln of u, because we have a 1 on. So if we minus a u from both sides, right, you see how the u's go away. And then we can integrate both sides, right? So if we integrate both sides, we'll get u ln of u minus u is equal to negative ln of y plus c. Substitute back in the x over y for our u's. So we have x over y ln x over y minus x over y equals negative ln of y plus c. And then the last thing we could do is just get c by itself. So we have x over y ln x over y minus x over y plus ln of y is equal to c. So all we did in this last step is move that negative ln of y to the left-hand side. All right, last problem from this section is problem number 28 from the review. This equation is already in standard form, so the integrating factor is, so integrating factor e, the negative integral of 4x dx, okay, is going to give us e to the negative 2x squared. So d dx is equal to, we have the integrating factor times y, which is e to the negative 2x squared sine x squared. Okay, and we're given an initial condition. Our initial condition is y of 0 is equal to 7. So if we integrate from 0 to x, d dt of e to the negative 2t squared y of t dt. Okay. So this is going to give me the integral from 0 to x of e to the negative 2t squared sine of t squared dt. So e to the negative 2x squared y of x minus e to the 0 y of 0. Since that there is 7, right? That was our initial y of 0 is 7. We can say that y of x is equal to 7e 2x squared plus e 2x squared integral from 0 to x of e to the negative 2t squared sine t squared dt.